All right, welcome. Welcome back from that exam. I hope you saw last week's video because last week we introduced the concept of fluids in motion, and we started looking at different types of descriptions of fluids and a little bit of math involved. And if you saw the math, you may have realized that it's not easy, right? It's not something that, oh, it's just 1 + 1 = 2. The math we're looking at when we're looking at fluids in motion involves derivatives, involves integrals. It's going to involve differential equations pretty soon, so hopefully our math is in good shape so that we can, more or less apply this. Now, this week and in the following, I would say, the next 3 weeks, we are going to start looking at how to apply some principles and some methods to study fluids. So if you remember from last week, we mentioned that there were 2 types of flow descriptions, right? Eulerian description that looks at control volumes in space, and a Lagrangian description that looks at systems, that looks at just fluid particles and follows them along as they move. Now, I'm going to start with more or less of an Eulerian description. I'm going to start by looking at control volumes in space and analyzing the fluid properties as they enter and as they leave those control volumes. We're going to find that that's an easier way to describe fluids because in order to study control volumes, essentially all we need to have is a good preparation in integrating. So as long as we know how to integrate and I guess how to derive, we should be able to study control volumes. There won't be any need to go into differential equations because we're not going to need differential equations, at least in this initial study of control volumes. So before we start deriving all these equations, I'm going to start with going over a couple of new terms that I would like to use from now on in this class. So I'm going to start by defining the flow or the flow rate. So if we recall week number 1, we said that a fluid is a substance that deforms continuously under a shear stress of any magnitude. And we mentioned that the deformation under a shear stress of any magnitude is what we call flow. So when I say flow as a property or flow rate, I'm looking at how much the fluid is deforming, right? But fluids deform continuously. So perhaps a measure of how much the fluid deforms is not helpful for us. Instead, let's look at a measure of how much the fluid deforms with respect to time. In other words, what is the flow rate of the fluid? So I can define flow rate, which I'll call in this class flow, which we can also call discharge, or which, if you want to be more specific, you can call it volumetric flow rate, as a time rate at which a volume of fluid flows through a cross-sectional area. In other words, a flow rate will be the amount of fluid that travels through some control surface or control area with respect to time, okay? If I want to write down flow rate, I can think of it as volume over time. At least in terms of dimensions, you can think of flow rate as volume over time. So let's look at a small control volume, just so that we can describe what flow rate is. So we're going to study a small control volume that lies on a streamline. So we have our streamline. Fluid is traveling through this streamline. But instead of studying the entire streamline, I only care to study the fluid that enters and leaves this little control volume. Okay, so we have the entire streamline, but we don't really care about the whole thing. We only care about whatever comes in and goes out of this little black box, which is our control volume. Now, if I study this fluid, you may have recalled from last class that we can study fluids in Cartesian coordinates. In other words, we can use an x, y, z coordinate system. Or we could also study fluids with respect to a streamline in what we call streamline coordinates. In other words, we can define a streamwise axis, which I'm going to call S, as an axis that's always tangent to my streamline. Now, this may be a little bit confusing because if you look at the shape of the streamline, then my S-axis actually changes depending on where my control volume is, right? If my control volume is here, my S-axis is actually pointing in this direction. If my control volume is here, my S-axis is actually pointing more or less in the horizontal direction. However, don't let this confuse you, because by setting your axis to be along a streamline, we're actually going to simplify our numbers, not actually make them harder. So if I set my S-axis to be along my streamline, bless you, then my normal axis will be the axis perpendicular to the s-axis that points towards the center of curvature. Once again, my normal axis will point towards the center of curvature along this curve, but once it starts to curve in the other direction, my n-axis will point in the opposite direction. So just as s changes direction, so does n change direction. But just because it changes doesn't mean it's going to be harder. We have a third axis, which is the y-axis, which points normal to this paper. So the y-axis, I'm not going to draw it here because you'll know that it's pointing normal to the paper. So why am I doing this? If we set our axis to be tangent to the streamline, and if we know that the streamline, the definition of a streamline is a line that's tangent to the velocity vector, then I'm essentially saying that my axis is tangent to the velocity vector. If my s-axis is tangent to my velocity vector, then I don't need to care about velocity components because the velocity will always be along the direction of my axis. And that's why I prefer, or we prefer, to use streamline coordinates. So let's now give some dimensions to this little control volume. This is a differentially small control volume. I'm going to blow it up here so you can see it a little bit bigger, but it's essentially a really, really small, differentially small control volume. Think of the differential analysis that we did in the previous weeks, right? We're thinking of something really, really, really small, so small that we can't really quantify with numbers. So if we can't really quantify with numbers, I'm going to give this control volume a differential dimension of ds along the streamwise direction. So along the s-axis, I'm going to give this a value of ds. And along the n-axis, I'm going to give this a dimension of dn. And I'm just going to try to draw it in 3 dimensions here. Along the y-axis, I'm just going to give this dimensions of dy. So there's my tiny control volume, ds, dn, dy. Very, very, very tiny control volume, so small that we can't even quantify it. Question: what is the differentially small volume of this element? What's the volume of that control volume? Thank you, right? ds times dn times dy. Thank you very much. Now, if I say, right, that this little control volume is located at my streamline, which means that the streamline passes through the control volume like this, then what would the cross-sectional area of the streamline be? In other words, if I'm traveling along the streamline, if I'm standing right here, surfing along my streamline, and I look at my control volume, I'm going to see a square. What is the area of that square? That's correct, dn times dy. Because essentially, what I'm looking at is an area that's normal to the streamline on this end and on the other end. So I want to get those 2 terms cleared up as quickly as possible so that now we can start using them. You see, if I were to calculate or express, right, the velocity component along the streamline, but we know that on a streamline, the velocity vector is tangent to the axis, which means that there is no component, it's the whole thing. Then I can define the velocity as simply a change in distance along the streamline with respect to time. Does this make sense? Velocity equals ds over dt, right? Because the fluid moves a distance of ds over a period of time dt. Okay? Good. So we have these 3 definitions for our little control volume. But now I don't want to find these. We all know what volume is. We all know what area is. We all know what velocity is. Instead, I'd like to find the flow passing through this little cube. In other words, fluid enters the control volume. It enters this cube, and then it leaves the cube as it travels through the streamline. The cube stays in the same place, but fluid enters and leaves it, right? So I can say that the flow, which I'm going to write down with the letter Q, the flow passing through this cube, since it's such a tiny, tiny, tiny cube, then I have a tiny, tiny, tiny flow or flow rate, okay? The definition of flow rate is an amount of volume, right, that is being transported over an amount of time. So far, so good. Volume over time. So if I say that fluid enters and fills up this container, What's the volume that's being transported? Thank you, dV, the volume of the control volume. And this volume is being transported over a tiny, tiny, tiny amount of time. But now we know that the volume of this control volume is simply ds times dn times dy. So I can simply express this as ds dn dy over my time. But now, here's where things get interesting. We also know that the fluid travels a small amount of distance s over a small amount of time. And what do we call that term? That's correct, velocity. So what we have is that ds over dt is simply the velocity of flow traveling through that little control volume. So I get that this is my velocity. And what's left? The dn times dy, which is simply my area. Now I'm going to call this element that I'm studying a control volume. Okay, so control volume is simply a volume that I'm studying. And I'm going to call the area through which the fluid is traveling. So the area where the fluid enters and or leaves, I'm going to call it my control surface. Okay. So surface, you think of an area. Volume, you think of a volume. So what we get is that the tiny, tiny, tiny amount of flow, Q, that travels through this streamline, or dq, sorry, is equal to the velocity times that little area, differential area A. But of course, this is differential analysis. This is for a tiny, tiny, tiny element. And we don't really care about tiny, tiny, tiny elements. We care about real, quantifiable fluid bodies. So can you tell me an example of a real, quantifiable fluid that travels?
River.
Sorry?
River.
Okay, flow through a river. So if we're looking at flow through a river, I'm just going to try to draw it in profile view. If we're looking at flow traveling through a river, then we don't really care about a tiny, tiny, tiny element. We care about flow over the entire river, right? So what I'm going to do is when I'm studying, right, a finite, a quantifiable fluid, I am going to try to quantify the amount of flow passing over some cross-sectional area A. Again, I was looking at flow passing through a tiny, 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 tiny area dA, but now I want flow that's passing through an actual area A. And then how do I find the total flow rate passing through that area? Well, I need to add up, right, all of the tiny, tiny, tiny flow rates. In other words, this area is made up of an infinite number of tiny, 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 tiny little control volumes, right? And each one of them has a tiny, tiny, tiny flow. So if I want the total flow, then I just have to add all of those up. How many dqs, how many tiny area dAs with dqs do we have in this finite quantifiable area? An infinite. So how can we add up an infinite number of elements? We integrate. Good. So the flow rate will simply be equal to the integral of dq, or if I use this definition right here, the integral of velocity times my dA evaluated over my finite area A. Okay? And that is flow rate. But that doesn't really tell us much. Remember when we did our fluid statics, we decided that we don't want to always integrate, right? Instead, we want to express things in equations that we can understand and that we can use. So I'm going to leave this expression here for now, but we're going to start to try to figure out different ways of expressing flow rate. Now, before I move any further, I do want to note that we have made some assumptions to arrive at this equation. And assumptions are not bad. As engineers, we're going to make a lot of assumptions. When I am modeling rivers, I make a lot of assumptions, right, to simplify my models. However, it's important to know which assumptions you made so that you can account for them whenever you cannot make those assumptions. Now here, my assumption is that my area dA is normal to my streamline. Can anybody explain to me what normal means? Exactly, orthogonal, right? So essentially perpendicular in every direction, right? So we're assuming that my cross-sectional area is normal to the streamline. However, there are cases where the area that you're studying is not normal to the streamline. It's not normal to the direction of flows. There are cases where I would like to study a fixed volume of fluid, but the streamlines actually change direction with time. So because of that, I cannot always say, or I cannot take it as a given, as a law, that my cross-sectional area, dA, is normal to the streamline. What we need to do then is account for an area that is not normal to a streamline. And here we're going to go a little bit into vector analysis. Does anybody know how to quantify an area in vector form? Have we done this before? I mean, have you done this before in your classes? How does that look? How does an area look in vector form?
Two vectors that aren't parallel, that you can define a plane.
Well, that's not really how I would use it. So in your higher level maths like calculus 3, we will define area vectors as simply a vector that points normal to the area. In other words, a vector that is orthogonal to your surface. Okay? In statics, I always tell my students that instead of visualizing vectors as simply these mathematical values that they need to operate on, I always ask them to please visualize vectors as products of scalars and directions. Because that's what vectors are. Vectors have magnitudes and direction. So based on that definition that I give my static students, the vector of an area is equal to the magnitude of that area, in other words, the area of your surface, multiplied by a unit vector that points normal to that surface. So if my area is this board, in which direction does that unit vector point? Towards you, right? If my area is this paper, in which direction does that vector point? Upwards, right? Good. So the area vector is simply equal to the magnitude of the area multiplied by a normal vector that points normal to the surface, okay? Now I want to do that because if I can express my area as vectors, then I can quantify any effects of any changes in direction between the streamline and the normal vector. So right now we assumed that the area, dA, was normal to the streamline. In other words, normal to the velocity vector. So if I were to draw my velocity vector here, and I wanted to draw my area vector, in which direction does my area vector for this face point? Right now, in which direction does the normal vector for this area point? Yeah, that's correct. Along the direction of the velocity, correct. In other words, bless you, my area vector and my velocity vector are pointing in the same direction, right? But now, there are cases, like we mentioned, where that's not what's happening, right? There are cases where my cross-sectional area and my velocity vector aren't going to point in the same direction. So I'm going to give an example. Let's try to look at an area. Just going to call it a tiny, tiny, tiny area dA with a normal vector that points normal to the surface. Okay? But instead of my streamline traveling normal to this area, I'm going to say that my streamline actually travels in this direction. So I'm studying an area that's inclined, basically. If I want to draw my velocity vector points along the direction of the streamline. Okay? Now, why am I doing this? Notice one thing. If we know the area vector, so if we know the direction of this area, the direction of the normal vector, and we know the direction of the streamline, then we can define the angle between the velocity vector and the area vector as theta. And we can say that that is simply the angle between the area and your velocity vector. Now, why am I doing this? When this happens, because we only care about the flow along the area, so we only care about dq as it travels along this area, then we don't need to use the entire velocity vector. We only need to use a component. And hopefully we can remember a little bit of our components. But if I were to ask you to calculate the velocity component along the area. How would you calculate that? That's right. Does everybody agree with him? Okay. So the velocity component, right, my velocity, is simply v cosine theta. And that's really what I care about. If you look at my definition of flow, it's simply the integral of v dA. So velocity as it passes through the area. But since the velocity in this case is not in the same direction as the area vector, then we need to only take the velocity component. So let's make that correction in this equation. My flow rate becomes the integral, not of v dA. What goes inside this integral now? If we want to account for an inclination in my area, exactly, v cosine theta dA. Correct. The component of velocity times dA. And now we can put everything we've learned about vectors into practice. There's a vector operation, right? That if I were to apply it to two vectors, I'm going to call them A and B. If I apply this operation to two vectors, the result is their magnitudes times the cosine of the angle between them. What's this operation? Yep, dot product, right? The dot product. If I take two vectors and I take the dot product between those two vectors, I essentially get the magnitudes of the two vectors and the cosine of the angle between them. And what are we looking at here? We have the magnitude of the velocity vector, that's v. We have the magnitude of my little area vector, dA. And we have the cosine of the angle between them. So can I say that this is actually just a dot product of two vectors? Yeah. So my flow rate becomes simply the dot product of the velocity vector and the differentially small area dA vector. So this will be the general definition of flow rate that I would like for you to use. Because this definition accounts for any inclination that there may be between the area and your streamline. So whenever you hear the words flow rate in this class, you're going to think of the integral of v dot dA. And of course, it's evaluated over your control surface. Any questions with flow rate? So when you see flow rate, think volume over time. Or if that's not possible, think v dot dA, integrated, okay? Now, of course, in engineering, like I said, we want to always try to simplify our problems so that we can use them. We can make them useful for us. So I'm going to walk you through some general simplifications that we will use in this class. First, let's say that our properties are uniform across an area. So we did rivers earlier. Let's say that we're looking at a pipe this time. We're looking at a pipe, water traveling through this pipe in this direction. And I'm studying essentially a circular area. If I say calculate the flow rate through this pipe, you could write this equation, Q equals integral of v dot dA. But what if the velocity at every single point in this area were the same? In other words, what if the properties across my area were uniform? In other words, at any point, if I were to pick any random dA, my v is still the same. Then this integral, if all of my properties are the same, this integral simply becomes v dot A. Okay? That's essentially what it becomes. Because if every single point in my area has the same velocity, then velocity is essentially a constant, right? And I just end up with the velocity and the integral of dA, which is just A. And why am I doing this? Well, we can simplify this even further. If we know that the streamline, the velocity vector, is normal to the area vector, then what's the angle between them? Between the area vector. Yeah, 0, right? Good. And what's the cosine of 0? Cosine of 0? 1. Good. So v dot A simply becomes my velocity times my area times the cosine of 0, or just v times a. So what we have here is a very, very simplified form of the flow rate equation, where flow rate is simply the velocity passing through an area multiplied by that area. So this is a simplification, but a very useful one that you're going to use after you graduate. So this simplification assumes uniform flow and an area normal to the streamline. So we have two definitions for flow rate. We have three. We have volume over time, we have the integral of v dot dA, and we have VA. Of course, which definition you choose to use really depends on what assumptions you can make for your system. So we're going to do a couple of problems. Well, you're going to do a couple of problems through your homework, through which you will have to decide which definition of flow rate to use. I would typically pick the easiest one, but remember that some of these definitions are a little bit limited. But this is I would say, a good definition of flow rate because it allows me to look at one thing. If the velocity is the same all over this area, and then Q equals VA. But what that tells me also is that the velocity is just equal to Q over A, right? We can jump from one to the other. But now, if the velocity is not the same, can we say this? If the velocity were to vary, we're looking at a pipe. We know that in real life, pipes have less velocity at the walls, more velocity at the center. So we cannot say that V is constant. So if V is not constant, and I still want to use this equation, what would this V be? Which one would you pick? Would you pick the lowest one? Would you pick the highest one? Which V can you pick if they're not the same in order for this equation to be true?
The average.
Exactly, the average, right? So if I want to write a more generalized definition, I can call this the average velocity, which is simply equal to Q over A. Now, I've had some students ask me some questions about the meaning of the average velocity, but think of it as an exam, right? Let's say that you got a 90 in your exam, and you got an 80 in your exam, right? And you got a 70 in your exam, okay? If I were to take the average of your 3 grades, what would that average be?
80.
80. How did you get that number?
You add them up and divide by.
You add them up and divide. Okay. Does that mean that you got 80 in the exam? No. Does that mean that you got 80 in your exam? No. However, what it does mean is that if the 3 of you would have gotten 80 in your exam, then the total sum will be the same, right? And that's exactly what's happening here. This average velocity doesn't mean that it's the velocity at the center. It doesn't mean that it's the velocity at the walls. But what it does mean is that if this entire area had one velocity only, it will still give you the same flow rate, okay? So that's what I say when I mean average velocity. These grades are not real. I'm just throwing out numbers, by the way. I just wanted to find easy numbers. So that's essentially what we need to know for flow. We're going to use it, right? And we're going to learn how to use it, and we're going to learn how to apply it. But for now, I'd like at least for us to know how to define it and how to find it, given some information. I'm going to define a second property called flux. Now, we've talked about flow as being volume over time, at least for this class and in our textbook, and in most textbooks that I've used, it's volume over time. But sometimes it's important to define the flux. Now, the flux, at least in terms of fluid mechanics, also called the mass flux, will be equal to a measure of mass that is being transported over time. In other words, flow looks at volume that's being transported. Flux looks at mass that is being transported. Now, just as a bit of a review, how do you think flow and flux could be related? If flow is the volume transported over time, flux is the mass transported over time, which fluid property can relate the two? Density, right? Good. So we know that at some point, we're going to have to deal with density. I like that fist bump you guys did there. That was nice. Okay? So flow, volume, flux, mass. But now let's figure out how we can define that flux. My friend Smith said that we need to look at density if we want to relate the two. So let's just look at density quickly. How do we define density? Exactly, right? Or if we want to get into the more specific details, right? dm over dv, okay? Now, if density is dm over dv, then I can find a differentially small element of mass by saying that dm is equal to density times a differentially small element of volume. Can we agree there? Do we agree here? dm equals rho dv? Good. So now I'm going to define my flux, which I write as m dot. That's Newtonian notation. I'm going to define my flux as simply an amount of mass that's transported over time. So dm over dt. But I know that my tiny, tiny, tiny mass, dm, is actually equal to density times a tiny volume. So I'll just write density times dv. And now what do I have? If we look at this, dv over dt is simply our tiny, tiny, tiny flow rate dq, right? So if dv over dt is our tiny, tiny, tiny flow rate dq, then I can say that mass flux, what am I missing here? Oh, I'm missing my differential. I can say that my differentially small mass flux is equal to the density times my dq, which we already defined as my velocity, times my d area. Now I can do the same thing I did earlier. This is just a tiny, tiny, tiny element. And if I want the entire mass, I can add the infinite number of tiny elements up, or I can just integrate. And if I integrate, right, I get that my mass flux is equal to the integral of rho v dA. Once again, what does this assume? This assumes that the area is normal to a streamline. So instead of using this definition, I'm going to use a more general definition where I consider the angle between the area vector and the streamline vector. And what that gives me is mass flux being equal to the integral over an area of density times my flow rate, v dot dA. So don't get too confused when you see this integral. Just look back at our definition of flow rate. We know that Q equals integral of v dot dA. So mass flux, as you can see here, is just rho dq. So it should be just rho times the integral of v dot dA. The reason I include my density inside my integral is because I can't assume that density is constant across an area. I cannot make that assumption. If I do, it may be right for some fluids, but not true for others. So because I can't assume that the density remains constant over the area, I'm going to keep it inside the integral. And this is the general definition of mass flux. Kind of feel bad for your class because we're just going to be going over these little integrals and definitions, whereas Thursday class is actually going to look at engineering applications. But sucks for you. Let's look at some simplifications, just like we did with flow rate, right? If we were to calculate mass flux, then we essentially need to integrate rho v dot dA, but sometimes we don't have to integrate. For example, we already said that if our flow is uniform, then my mass flux, I'm going to write it down here. Then my mass flux is simply equal to rho v dot A. Because for flow rate, if my properties were uniform, then my integral simply becomes v dot A. So here it just becomes rho v dot A. But now, if my area is normal, right, to the streamline, looking at how the flow is simplified, what do you think my mass flux will look like if my area is also normal to the streamline? So we look at flow rate. We see the simplifications we made to land at this equation. We want to apply the same simplifications to land at an equation, but for mass flux. So what do you think that equation will look like? Exactly. Density times velocity times area. And here, what we have is a very general, right, simplification for mass flux. If we look, Q, flow rate, equals V times A. So this is also equal to simply density times flow rate. So we have three definitions for mass flux. And again, you will choose to use whichever one is easiest for you given the data that you have available. Any questions with the ideas or the concepts of flow and flux? Are we good on flow and flux? Julia, what's flow?
Flow is volume over time.
What's flux, Ethan?
It's the amount of mass over time.
Exactly. One is volume over time, one is mass over time. Who's ready for some calculus? Yay. Good. We're studying, like I said, control volumes, right? We're studying these little positions, these little volumes, where I only look at the fluid that comes in and the fluid that leaves, okay? Now, earlier or last week actually, earlier in the class, so last week, I mentioned that there are two approaches to study fluids. The one we call the Eulerian approach, which looks at control volumes, and the one that we call the Lagrangian approach, which looks at systems, which looks at fixed quantities of mass. So I'm going to try to properly define these terms, systems and control volumes, so that we can use these definitions to come up with a more general equation that we can use. So a system, and this was probably defined in week 2 as well, so we're just going to recap it, but a system is a fixed quantity of mass that I'm studying. In other words, if I'm studying these fluid particles, let's say that I'm looking at a fixed quantity of fluid particles at, let's say time equals 0. Time equals t. But then at time equals t plus delta t, my fluid particles have moved elsewhere. Perhaps they have mixed with other fluid particles. I'm going to write the other ones as simply these darker colored fluid particles. So based on the definition of a system, if I'm studying a fixed quantity of mass, a fixed quantity of matter, that means that I only care about these particles, regardless of where they are. I'm going to follow these particles and not care, or at least not study anything that's outside of these particles. So a system is a fixed quantity of matter, and notice that we can have flows where the system intermingles with other particles that are not part of it. As we can see here, we have these little blue particles, and as time passes, they mix with other particles, but our system is still the blue particles. Does that make sense? System, you follow the particles. They can move away from each other, they can move towards each other, but you follow the particles and only the particles, okay? On the other hand, a control volume is a volume, right? Of course. Is a volume that's being studied. I would like to say a fixed volume, but we'll learn later that we can actually increase and decrease the magnitude of our control volume. So the volume is simply a location in space that we are studying. That location can change, it can move, but it's up to you whether it changes or moves. It's not up to the fluid. So a control volume is a volume being studied. In other words, if I'm looking at this volume being studied and I have fluid particles traveling in but also out of this volume, it doesn't matter at what time I'm looking at. I only care about the volumes, the particles that are inside the volume. I don't care about the ones that are outside before they enter. I don't care about the ones that are outside after they leave. I only care about the particles inside the control volume. Does that make sense? So system, you follow the particles. Control volume, you follow the region in space or the volume, okay? Now, we already said that the fluid enters and leaves the control volume through a control surface. So I'm not sure I have to define it here, but essentially a control surface, which is also known as the boundary, is simply the area where fluid enters and leaves your control volume. So in this case, if my fluid is entering and leaving through this area, then this will be my control surface, and perhaps this will be my control surface. A control volume can be made of only control surfaces, or it can have some of its sides as control surfaces. It's all up to you, up to the person that's actually studying the fluids. So with these definitions, we're going to see how we can transform what's essentially a system definition or a system study into a control volume study. Now, why do we need this? In class, we said in week number 2, we went over some basic laws of conservation. I'm going to recap them here if you don't remember them from week 2. We said that all fluids abide by these laws. I think the first law, we said that the conservation of mass. And what does the conservation of mass say? Well, a system is a fixed, I'm going to note that word, quantity of mass, right? So the change in mass in a system with respect to time is what? I'm going to go back. The system is a fixed quantity of mass. So the change in mass in a system is what? 0, right? There is no change because this is a fixed quantity of mass, so it doesn't change. So the conservation of mass law tells us that the change in mass with respect to time in a system is 0. The conservation of momentum tells us that the change in momentum with respect to time in a system is equal to the sum of forces acting on that system. That is Newton's second law of motion. And the conservation of energy tells us that the change in energy with respect to time in a system is equal to the work and the heat transfer rate. Now, you don't have to memorize these now. We're actually going to dedicate an entire week, well, one day for this one, but an entire week for momentum and energy. So you don't have to memorize them now, but I did want to recap them. So if you need more information, you can always go back to your week 2 lecture notes, okay? Now, why do I care about this system and control volume? Because these laws of conservation apply to systems, right? These laws of conservation apply to systems. But we'll see that control volumes are actually easier to study, a lot easier to study than systems. So then the question is, how can we take these 3 laws and how can we transform them into control volume laws? Because systems are fixed quantities of matter, but control volumes aren't. So if you look at a control volume, right, I can't really say that the change of mass with respect to time in a control volume is 0, because mass can enter and it can leave as it pleases, right? So I can't just rewrite these and apply them into my control volume. I need to transform them. And hopefully, in the remaining 30 minutes or 27 minutes in the class, we will come up with a way to transform our system equations into control volume equations. I'm going to give you 30 seconds to breathe and internalize all of the calculus you've learned in your first year of college. So let's take some time to breathe and internalize our calculus, because we are going to use it now. And I think if you help me, then we can actually finish faster, okay? So we know that the properties of a fluid, if you have, has anyone taken thermodynamics? No? You're taking it, okay. So you know that in thermodynamics we have properties of fluids that depend on the amount, or properties of anything that depend on the amount of substance and that depend on mass, and properties that don't depend on mass, right? So if you haven't taken thermo, it's okay. We're going to go over this a little bit today. We are going to say that the properties that depend on mass are extensive properties. Does that ring a bell? Okay, extensive properties. So extensive properties are properties that depend on mass. Now, for this study, I don't want to focus on any one property. I mean, I can focus on momentum, I can focus on energy, but instead of focusing on one specific property, I'm just going to give a random variable, just capital N, and N can represent any extensive property, okay? So an extensive property is one that depends on mass, and an example of any extensive property includes momentum, for example, which is just mass times velocity. Can you give me another example of an extensive property? What properties depend on mass? In other words, if the mass changes, the property changes. There we go, energy, right? That's good. So those are our extensive properties. I'm going to define intensive properties as what? Yeah, the ones that don't depend on mass. Good. And again, because I don't want to look at just one property, I want this definition or this derivation to apply to any property. I'm going to give my intensive property a variable of eta, or if you're in fraternity Greek, eta. Okay? So if they don't depend on mass, how can we get an intensive property? Essentially, an intensive property is simply equal to the extensive property, I'm just going to call it n, divided by its mass. So let's look at some examples of intensive property. If momentum is an extensive property, what do you think is the corresponding intensive property?
Velocity.
Velocity, right? Because we saw that intensive properties are simply extensive properties divided over mass. So the intensive property of momentum is velocity. And if you're confused, well, think of it this way. Eta is equal to n over mass. And in this case, my extensive property is momentum, which is m times v over mass. And this just gives me velocity. For energy, if you haven't thinking thermal, then it's okay. The corresponding intensive property is called specific energy. And we typically write the specific energy with a lowercase e, which is simply the energy divided by its mass. Now be thankful that this is not a thermal class. However, we do have an entire week that's called conservation of energy. So we will look into these properties a little bit. But the reason I'm looking at extensive and intensive properties is because these will be important in our transformation from systems to control volumes, okay? So first, let's look at the relationship between extensive and intensive properties. If eta is any intensive property, right, then I know that eta is simply equal to my extensive property over mass. However, if my property is not equally distributed across a mass, then I can't really just write n over m. I need to write it in derivative form. That's simply to account for any non-uniformity that occurs or exists in our mass. Now, from this definition of an intensive property, I'm going to say that a tiny bit of extensive property, it can be momentum. Maybe think of energy. Energy, I think, would be an easier one to think of. A tiny bit of energy is equal to the specific energy, that's eta, times a tiny, tiny, tiny amount of mass. So a tiny bit of extensive property is equal to the intensive property times the tiny, tiny, tiny amount of mass. And from here, we go back to our calculus, right? How do we find the entire bit of extensive property acting over a system, acting over a mass? We integrate, right? So we integrate eta dm over and mass. Good. Now in fluids, you may have seen or you may have heard me mention the first couple of weeks. In fluids, using mass is not really that helpful. Instead, we always want to express things in terms of volumes. So if you go back to your notes just a few minutes ago, how do we relate mass to volume? Density, right? And what was the relationship? What was a little bit of dm equal to? We wrote this just a few seconds ago.
Density dV.
There we go. Density times a tiny volume, right? So I'm writing this as a little cloud to be a reminder. But the reason I want this to be a reminder is because we can find that extensive property as simply equal to the integral of my intensive property. But instead of writing it across a tiny differential mass element, I'm going to write it times density times a tiny volume element. Okay, so that's the definition that I want to get at. That's the definition that I want you to think of when you think of extensive and intensive property relationships. Okay, so extensive property is simply the integral of eta times density times my tiny volume dV. And now things are going to get a little bit ugly. We have 20 minutes, a little bit less than 20 minutes. Hopefully in this little bit less than 20 minutes, we're going to derive a beautiful, beautiful, beautiful formulation that then the Thursday class can enjoy and use. But you will have to watch the video for Thursday in order to enjoy it yourselves. Let's think of a system and think of a control volume. And I guess to make things easier, I'm going to use red for my system. And I'll try to use blue for my control volume. So let's say that I'm studying a system. I'm studying a fixed quantity of fluid particles. Okay? I'm going to draw my fixed quantity of fluid particles. And let's say that those fixed quantity of fluid particles are right here. So I'm studying a system. I'm Mr. Lagrange, and I'm studying using my Lagrangian approach. But now Mr. Euler comes, and he says, well, no, I would like to study a control volume. So Euler decides to study a control volume. Now, at time equals t, so at our first time step, my system and my control volume are basically covering the same amount of fluid. Okay, so I'm studying a fixed amount of fluid particles, and the control volume actually covers just those fixed amount of fluid particles. So at time equals t, the fluid in my system and the fluid in my control volume are exactly the same. However, fluids move, or at least if we want the class to be fun, fluids have to move. So at a later time t plus dt, my system has moved. Let's say my system is now elsewhere. Ethan, if my system starts to shift, does my control volume move with it? No? Okay, good. So my control volume doesn't move. So at time t plus dt, my system has moved, but my control volume has not moved. Good? So what do we have? We have a control volume that consists of part of the system plus a new amount of fluid. I'm going to call this new amount of fluid my region that went into my control volume. I don't know what to call it, just Rn, okay? Region that is now in the control volume. I can also say that my system, or part of my system, is now outside of my control volume. So I'm going to call that part of the system that's outside of the control volume, I'm just going to call it my region that left the control volume. So far, is everybody understanding these terms? Do you understand why we're calling these lines R in? Do you understand why we're calling these little dots outside R out? Good. So what we have is at time t plus dt, we have a system and a control volume that are not at the same location. We have a control volume that has part of the system but not the whole thing. We have a system which is partially inside a control volume, but not fully inside a control volume. Okay? So now let's look at our two types of descriptions. In the Lagrangian description, that is in the system view, I can define any change in any extensive property with respect to time. That's simply the derivative of my property with respect to time. Now, I'm not going to ask you to tell me, but just so you remember, your derivatives are simply limits, right? Limit as delta t equals 0, because our derivative is taken with respect to time, of my extensive property at t plus dt minus my extensive property at t divided by the finite change in time delta t. So we have essentially a derivative of n with respect to time, and we express this derivative as a limit, which is simply how we normally calculate derivatives in calculus, okay? Now that is Lagrangian. However, if we're looking at the control volume, in other words, if we're looking at the Eulerian view, then the rate of change, right, the change in extensive property with respect to time won't be just this derivative. It's going to have to consider how much property left the volume, how much property entered the volume. So first, let's try to review a little bit. In the Eulerian description, so in terms of my control volume, at time t, okay, at time t, what region does the system occupy? So at time t, what region does the system occupy? Where is the system at time t? Inside the control volume. So at time t, my system is in my control volume, okay? However, at time t plus delta t, right, my system is not in my control volume. Rather, part of it is in my control volume. So it occupies the control volume region, but it also occupies the R out, the outer region. But it does not occupy the inner region. Does that make sense? At time t plus delta t, my system is in the control volume, plus it's also in the outer region, but it's not in this little Rn region, right? So my system equals, or my system is in CV plus R out minus Rn, okay? We're getting somewhere. And why are we getting somewhere? Because now that we know where my system is in the control volume, I can now take, in terms of control volume, the derivative of an extensive property with respect to time. I can't just write this limit, because this limit assumes that we're always following the same particles. But here we're not just following the same particles, we are following a control volume. So my derivative becomes the limit as delta t approaches 0 of what? Well, it becomes the limit of my property at time t plus dt minus my property at time t, so just like what we have here, over delta t. So what is my property at time t plus dt? We'll have the extensive property inside the control volume at time t plus dt, or delta t, sorry. Let's see, we have CV, plus we have the extensive property in my outer region. So I'm going to put plus my delta n out. Minus, we have the extensive property in my inner region. That's not part of the system, so minus n in. And then minus, right, minus the extensive property at time t. And at time t, my extensive property is simply the extensive property at my control volume. Okay? And all of this over delta t. 11 minutes more. In 11 minutes, we should get to an actual equation. Now, what I'm going to do is I'm going to take this derivative, and I'm going to rearrange it a little bit. I'm going to keep all of my control volume terms on one side, and I'm going to keep these in and out terms on the other. So I can express this derivative as the limit as delta t approaches 0, right, of my control volume terms. So I'm going to write my control volume, and you'll see why I am rearranging them in this way. Over delta t plus the limit as delta t approaches 0 minus the limit as delta t approaches 0. Notice that the further we get to the end of the class, the worse my handwriting gets, because I am trying to finish quickly, okay? So why am I rearranging them this way? Because now we can look at these terms individually. First off, you know from the definition of a derivative, right, that the limit as delta t equals 0 of n at t plus dt minus n at t over delta t is simply my derivative dn over dt. So look at this system equation and now compare it to this first term. What is this first term? It's simply a derivative, because we have here a derivative, right? The property at t plus delta t minus the property at t over dt. The property at t plus delta t minus the property at t over dt. We have what's essentially the same derivative. So I can express all of this term as simply the derivative of my extensive property over the control volume, because we do need to consider this at the control volume, with respect to time. Why am I writing these derivatives as squiggly lines? What does that mean? Partial derivatives, right? Because we know that in terms of control volumes, we don't only care about time, but we also care about space. So my derivative will have to be a partial derivative, because this is only the derivative with respect to time. Good. So we get that. We look at these two other derivatives. We have the limit, right, or the limit as delta t approaches 0 of delta n out over delta t, and we have the same thing for the n entering. But now, let's think of the following. Let's see, where can I write a little thought bubble here? We know that delta n over delta t can be the same as simply my intensive property times a change in mass over delta t. So this comes from our definition of an intensive and extensive property, right? So if we have a finite change in my extensive property, then essentially that's a finite change in my intensive property, which we can also express in terms of volume. Okay? So why am I asking you to remember this? Because now we see that the change in extensive property with respect to time is actually equal to the intensive property times the density times a finite change of volume with respect to time. And what is a change in volume with respect to time? A flow rate, right? So what do we get? The change in extensive property with respect to time is actually directly related to the flow rate. It's actually equal to the intensive property times the density times the flow rate. So if I want to write it in integral form, if you don't remember, that's fine. We can go ahead and review our definition of a flow rate. Our definition of flow rate is integral of v dot dA. So we can write now this limit, we can write it as an integral. What integral? Well, the integral of the extensive property times density times whatever goes inside the flow rate integral. So in this case, it will be intensive property times density. And what was flow rate again? Yep, v dot dA. And this will all be evaluated across an area. Now, of course, this is for the fluid leaving, so we need to consider the velocity leaving and the area where the fluid is leaving your control volume. Okay? And we have minus, and we can write the same thing. What we have here is essentially the integral of my intensive property times my density times my velocity entering the control volume dot my d area entering the control volume evaluated over an area. So now I am getting somewhere, because I get that for my control volume, my change dn over dt is equal to the partial change of my extensive property with respect to time across the control volume plus the intensive property multiplied by the density multiplied by the flow rate leaving minus the intensive property multiplied by the density multiplied by the flow rate entering. And now I can express this equation in its final form. The partial change, let me try to organize this a little bit. There we go. The partial change of my extensive property with respect to time can be looked at, right, or can be expressed in integral form. So how? Remember that the extensive property was equal, right, to the integral of my intensive property times density times dV. So I can express this partial change as the partial change over time of my extensive property, which is just the integral of my intensive property times density times dV, evaluated over my control volume. So now I can express this term as my integral form. And finally, I get that the change in my extensive property with respect to time is equal to the partial change with respect to time of the integral of my intensive property times density evaluated over my control volume, right? It's evaluated over a volume dV. Plus, I have my integrals across my control surfaces, leaving and entering. So I can say, or I can combine these two integrals to simply just one integral evaluated across the entire control surface. Because we said that the areas where fluid enters and leaves the control volume is what we call the control surface. So plus, we have the integral of my extensive property times density times velocity dot dA, and this is evaluated over the entire cross control surface, what enters as well as what leaves. And this wonderful clean equation is called the Reynolds transport theorem. Now, why is the Reynolds transport theorem important? The Reynolds transport theorem is going to help us convert extensive or system properties, system laws, such as the conservation of mass, momentum, and energy, into a control volume equation. So whenever we're looking or studying control volumes, this is the equation that we have to start with for any study of control volume. So the Reynolds transport theorem will be our tool for creating equations for our control volumes. You know, I don't encourage memorizing equations. However, I will say that if you don't want to rederive the Reynolds transport theorem every time you try to use it, then at least try to remember these terms. Remember that we have a change with respect to time across the control volume, and then we have the integral across the control surface. As long as you understand those two terms, applying the Reynolds transport theorem will be easy. Any questions? All right, so now we're going to look at some engineering class is over. So I guess you got to go. And next class, we'll look at some fun engineering applications.